Recording.
Hi, sir. My name is Suryan Sehgal, 19 BC 1465. I'll be speaking on some topics like cryptographic hash function, properties of hash function, and SHA-256 hash function as my digital assignment too. So here I start. I hope you can see the video. And now I'll be speaking about the cryptographic hash functions. A hash function is a mathematical function with the following properties. Its input can be of any string of any size. It produces a fixed sized output. It is efficiently computable. For a hash function to be cryptographically secure, we have three properties: collision resistance, hiding, and puzzle friendliness. The property one is collision resistance. A collision occurs when two distinct inputs produces the same output. If we inputted X and Y and both are giving the same output Z, we call it a collision. A hash function is collision resistance if nobody can find a collision. Collision resistance. A hash function H is said to be collision resistant if it is infeasible to find two values X and Y such that X is not equal to Y, but yet hash function of X is equal to hash function of Y. Actually, collisions exist for any hash function, and we can prove this by a simple counting argument. The input space to the hash function contains all strings of all lengths, yet the output space contains only strings of a specific fixed length. This means that the input space is very large as compared to the output space. And inevitability of collision is basically if we consider the following simple method for finding a collision for a hash function with 256-bit output size. To pick 2 power 256 plus 1 distinct values, we compute the hashes of each of them and check whether any two outputs are equal. Since we picked more inputs than possible outputs, some pair must collide when you apply the hash function. As you can see in the picture also, the possible inputs are pretty large as compared to the possible outputs cloud. So hence, we can assume that there will be some collisions in the future that will be found. Consider, for example, the following hash function. Hash of x is equal to x mod 2 power 256. This function meets the requirements of a hash function as it accepts inputs of any length, returns a fixed size output, 256 bits, and is efficiently computable. But this function also has an efficient method for finding a collision. Notice that this function just returns the last 256 bits of output. One collision then would be values 3, and 3 plus 2 power 256 is pretty large. Application of this property collision resistance is a normal message digest. If we consider Secure Box is an application which is authenticated online file storage system that allows user to upload files to ensure their integrity when they upload them. Suppose that Alice uploads a really large file and she wants to able to verify the later file she downloads is the same as one she uploaded. One way to do that is to save the whole big file locally and directly compare it to the file she downloads. While this works, it largely defeats the purpose of uploading the file in the first place. If Alice needs to access the local copy of the file to ensure its integrity, she can use the local copy directly. And by using the local copy directly, there is a solution which can be done. Hash pointer is the best solution in this. A hash pointer is used to basically keep the information of the data and also the location of the large file that she has uploaded. So if there is any change in the hash function, it means there has been tampering or modification done to the original document. So she would get to know easily just by comparing the hash function of both the file, like the later she downloaded and now what is the difference between the hash function. Property 2 is hiding. The hiding property asserts that if we are given the output of the hash function y is equal to hash of x, there's no feasible way to figure out what the input x was. The problem is this property can't be true in the form stated. Consider the following simple example. If we are gonna experiment where we flip a coin, if the result of the coin comes heads, we are gonna announce the hash of the string is head. If the result was tails, we are gonna announce the hash of the string is tails. Hiding a hash function h is said to be in hiding when we Choose a secret value R, which is from a probability distribution that has high minimum entropy. High minimum entropy means probability of predicting outcome, and high minimum entropy means it has been taken out of a widely spread out data. Then the given hash of R concatenated with X, it will be infeasible to find X, where double bars shows the concatenation. In information theory, minimum entropy is a measure of how predictable an outcome is, and high minimum entropy captures the intuitive idea that the distribution is very spread out. Application is commitments. A commitment is a digital analog of taking a value, sealing it in an envelope, and putting the envelope out on the table where everyone can see it. Commitment scheme has two properties. One is com means commit message comma nonce. The commit function takes a message and a secret random value called nonce as input and returns a commitment. Verify comma message comma nonce. The verify function takes a commitment nonce and message as input. It returns true if com equal to commit message nonce and false otherwise. Every time you commit to a value, it is important that you choose a random value nonce. In cryptography, the term nonce is used to refer to a secret value that can be only used once. If we take another look to the property required of our commitment scheme, if we substitute the instantiation of commit and verify as well as hash function of nonce concatenated with message for com, then these property will become as follows. These properties will follow two properties: hiding, where we can't find the message, and binding. Binding is like similar to collision resistance, as it is infeasible to find any two pairs with the same hash function but different messages. Third property is puzzle friendliness. Puzzle friendliness is a hash function h is said to be in puzzle friendliness where every n bit output value y, if k is chosen from a distribution with high minimum entropy, then it is infeasible to find x such that h k concatenation x belongs to y in significantly less than 2 power n time. One application of puzzle friendliness is search puzzle. A search puzzle is nowadays used in mathematical problem. A search puzzle consists of a hash function, a value ID, which we call the puzzle ID, as it is chosen from a high minimum entropy, well distributed data, and a target set y. The solution to this puzzle is value x, such that h ID concatenated with x belongs to y. Now we talk about SHA-256. SHA-256 is a hash function that is particularly used for a Bitcoin transaction. As we have discussed all the properties of a hash function application, and now we'll discuss about a particular hash function used primarily for Bitcoin transaction. As long as we can build a hash function that works on a fixed length input, there's a generic method to convert it into a hash function that works on arbitrary length input. It is called the Merkle-Diamond transform. SHA-256 is one of a number, like it is one of the most commonly used hash functions that make use of this method. In common terminology, the underlying fixed length collision resistant me is known as a compression function. It has been proven that if the compression function is collision resistant, then overall hash function is collision resistance as well. In common layman language, the fixed length collision resistant hash function is known as compression function. As we know that SHA-256 uses Merkle-Diamond transformation, and Merkle-Diamond transform is quite simple. If you suppose that the compression function takes an input of length m and produces an output of smaller length n, the input to the hash function, which can be of any size, is divided into block of lengths m minus n. The construction work as follows: if we pass each blocks together with the output of the previous block into the compression function, we'll be noticing that the input length then be m minus n plus n is equal to m, which is the input length is equal to the output length of the compression function. As we can see in the diagram, IV stands for the initialization vector, and 256 bits has been inputted in it. And as we can see, the block 1 message size is 5 into bits. So now, if we use the same formula, 256 plus 5 into minus 5 into, it gives back again 256 bits. It means that the compression function has equal size of input and it outputs the equal size of output. This is the main application and the main diagram used for SHA-256 hash function. Thank you.